Okay, hello everybody. So today we're going to talk of the some other new consequences. Well, new in the sense that new to our course, of course, of special relativity. We're going to talk of mass, energy, and momentum in special relativity. Uh, I suppose you remember how mass was varying with velocity, right? So unlike in classical mechanics where if you whatever the mass of a body is, if you move, if the body moves, its mass doesn't change. But here of course we have this concept of what a rest mass is, and the fact that you are in a frame which is moving with some some uniform velocity with something else, and in a sense the mass itself is moving with certain velocity, then you do find the mass of the body has changed. Well, we did see some consequences of that. Today what we're going to do is relate the mass, that is, to the total energy and also with the momentum. Okay. Now, having talked of mass and energy, I mean, it's very certain that we're going to talk of E is equal to mc squared. We're going to spend some time to see how this comes about. It's, I suppose, one of the most well-known equations in physics. Anybody who has even opened a textbook in physics or read about scientists and what physics is has heard about this equation. So today what we're going to do is to see in a simple way how to derive this from principles which are known to us. Okay. So first, let's consider a force which is being applied to body, and when this force acts, what happens is that it displaces the body by a small amount dx, let's say, in time dt. Okay, so the small displacement dx, and that too in the direction of the force. Why? So if you take the dot product, if you just take, you don't need to take the vector part, it's just f dx. Okay. And then it also happens in some small time dt, right? So what happens? I mean, what happens when one applies this force? Well, the body starts moving. I mean, if the body was initially at rest and then after the application of the force it attains a velocity v, let's say small v, then what would be the total gain in the kinetic energy of the body? Well, by definition it's the work done, isn't it? I mean, so that's the energy that the kinetic energy that the body has gained once it reaches a final velocity v from its initial rest position. Okay, and what is that? So that's integration of f dx. Okay. Of course, well, in a proper sense, one should have taken the vector f dot dx, but as we said, the displacement is in the direction of the force, so it hardly matters here. Now, the interesting point here is that we write this force now in terms of the rate of change of momentum. Okay, just see the region next to f dx, and you see that it's under the integral sign you have dp dt, so that p being the momentum gained, okay, and dx is the displacement anyway. So how do you write this momentum? You know that momentum is the mass times the velocity. So we write d of dt of mv, okay, and then for dx we just write v dt. Now why is that? So v being the velocity of the body, that's equal to dx by dt, and then we have just replaced dx as v dt, right? So how does I mean, what does the equation for the expression for the kinetic energy boils down to? Well, it's, as we said, I mean, we are finding the gain in the kinetic energy when the particle is has moved from its rest position to its and has attained the final velocity v. It's the integral within the limits 0 to v, v being the final velocity gained, and in the integrand is v of d of mv. Now, check that here we have not talked of whether m is constant or not. Okay. So, this form of the kinetic energy is very standard. We can use it, for example, let's why don't we use it to find the non-relativistic equation, non-relativistic expression for the kinetic energy. That will clarify the situation a bit. So, for the non-relativistic case, what do we do? Here we know that mass of a body is constant. I mean, it's a fixed thing. So, we can take it out of the differential d of mv, take it out of the integral sign, so that the integration for the kinetic energy is simply v dv, and then from 0 to the final velocity at the end. It's a very simple integration to do. The integral rather becomes v square by 2, v dv 0 to v, that becomes v square by 2. So, the total kinetic energy is nothing but half mv square. Now, this is a known expression to us. I mean, we know this expression, half mv square. It's used almost everywhere in classical physics, classical mechanics, by the way. So, of course, what have we done here? We have taken the mass to be a constant thing, so as expected. Now, what happens to the relativistic case? In the relativistic case, remember that the mass is indeed a function of velocity. Okay? So, if the mass of course moves, if the body moves with a certain velocity, with a large velocity, we do see actually large as compared to what? I mean, if it is, of course, all velocities we will be considering is less than the speed of light, but then if it's approaching the speed of light, we do see that the mass has increased by a lot. Okay, of course, I mean, when we're at very low speeds, it doesn't matter. Okay, so we are still in the non-relativistic limit, but then we have appreciable speeds, then we do start feeling that the mass of the body has increased. Okay, so what happens if we consider that? So, the mass of a body being a function of the velocity now. Okay, then we can no longer take the mass or the m out of the differential, and then we have to use the entire thing. Okay. Now, what would be the expression? Okay, you're going to put in the exact value of the momentum or the exact value of the mass here, that is m0 divided by root over of 1 minus v square by c square. Of course, the v is there. Okay. So, the kinetic energy, and what is m0 here? m0 is the rest mass. Okay, that is the mass of the body that is measured when the body is at rest. Okay. So, what is the expression for the kinetic energy then? Well, it is v times d of m0 v divided by root over of 1 minus v square by c square. Okay. Now, this might look like a bit complicated, but we do have a thing called integration by parts in mathematics, and so I think it's a proper case to utilize such a trick. Okay. So, what is this integration by parts? So, it is that if you have an integration of x dy, and then you can write this as and then y is some complicated function that you have. So, it is nothing but xy minus of integral of y dx. Okay. Now, what we do is that we identify x as the velocity here, and then for y we take it's m times, that is the momentum. So, m times v, that is nothing but m0 v divided by root over of 1 minus v square by c square. Okay, so let us just do this integration and then get the result. If you are interested in the algebra of it, I am going to spend one more slide on it. So, just to show you some of the steps. Okay. So, 1 or 2 slides, that is. So, the integration that we are going to do is one written at the bottom of your screen. Okay. So, that is the expression for the relativistic case when mass is a function of velocity. So, the kinetic energy happens to be m0 v square divided by 1 minus v square by c square, square root of that, minus of m0, and then we take the integral of v dv divided by root over of 1 minus v square by c square. So, if you do this integral and then put in the proper limits, okay, just look at the second line. So, when you do the integral and put in the proper limits, so you get the one that is given in the brackets there, that is m0 c square divided by into root over of 1 minus v square by c square, and then the limits from 0 to v. And then the whole expression simplifies, so whole expression for the kinetic energy simplifies into two parts. See that it simplifies into an expression for the mass of a body which is moving with a certain velocity v times c square. Why? The mass of the body being m0 divided by root over of 1 minus v square by c square, that is the total mass of a body when it is moving at a certain velocity v, that is multiplied by c square minus then m0, now m0 is what? m0 is just the rest mass, okay, of the body times c square, c being the velocity of light. Okay. So, that is what we have, that is the total kinetic energy of the body. Okay. Now, kinetic energy of the body being that, we can interpret the total energy of the body as something like m0 divided by root over 1 minus v square by c square, okay, times the c square. Okay. So, that will be then equal to m0 c square, we call it as the rest mass energy if we consider m c square as the total energy plus the kinetic energy. Okay. If that sounds a bit confusing, it might a little bit. Let us just have a look at the next slide and that will clarify our concept. What is it? So, at rest, when the body is at rest, we know the kinetic energy is 0, okay. But what happens to the total energy? Remember, if you go back to our old slide, we see that when the body is at rest, the total kinetic energy is 0, but the total energy is still m0 c square when the body is at rest. So, that justifies the word that justifies the term rest mass energy. That is the intrinsic energy associated with the body even when it is at rest. So, when the body starts moving, the total energy would be this intrinsic rest mass energy plus whatever kinetic energy the body has gained. So, that will be then the total energy. Okay. So, that is exactly what we meant by saying that we interpret the total energy as m c square and m being m0 divided by 1 minus v square by c square. Okay. So, having known this concept of what a rest mass energy is, let us just write that as E0, okay, just to signify that it is in the rest frame of the body or the energy of the body when the body is at rest. So, as you said, what is the total energy of the body when the object is moving? It will be E, that will be equal to E0 times plus the kinetic energy, that is, and what is that? That is nothing but m0 root over 1 minus v square by c square times c square. Okay. And what is that? That is simply m c square, where m is the relativistic mass. Okay. So, you see how this E equal to m c square has come about. Okay. Now, of course, this is a profound result. I mean, it has not only altered physics, it has altered the world actually. Okay. So, it is the first time you are seeing that the intrinsic mass is being related with the energy of the body, and it has immense consequences in fields of in other branches of physics. Okay. For example, if we consider the energy production in the sun, for example, their energy is being produced by fusing hydrogen into helium. Okay. So, if you add up the masses of hydrogen and you add up the masses of helium, okay, you would find that in the final product the total mass is not the same. I mean, whatever you started, the total amount of hydrogen, the total mass of the hydrogen you started, okay, and the total mass of helium that is produced, you will see it is less. So, where has this mass gone into? Well, this mass has been converted into energy. Okay. So, hydrogen is being fused into helium and then some amount of energy is released. Okay, and that's the source of that. Well, that's more or less the, you know, the source of energy production in the sun. And just to give you an example, you know, just to feel of the numbers or the amount of energy that's being converted uh, from matter uh, per second. Okay, uh, about uh, about 4.4 into 10 to the power 9 kilograms of matter is being converted to energy per second in the sun. Okay, so how are you going to find the total energy released per second? That's the total power actually. So you're going to multiply this number 4.4 into 10 to the power 9, okay, kg per second, into 3 into 10 to the power 8 meter per second square, okay, meter per second, that is, I'm sorry, meter per second, and take the square of that, then what do you find? You would find that the total energy is nothing but 4 into 10 to the power 26 joule per second. Okay. Now, if you just consider the 1000-watt bulb, okay, I remember nobody uses 1000-watt bulbs in their homes anymore. You'd rather use more efficient sources. Okay, but let's, you know, how bright a 1000-watt bulb can be. Okay, that's 10 to the power 3. Okay, that's 10 to the power 3 watts. If you divide 4 into 10 to the power 26 by 20 to the power 3, it's nothing but 4 into 10 to the power 23. So per second, the sun is shining like 4 into 10 to the power 23,000-watt bulbs. Just have a feel. I just have a feeling of how large this power is. Well, actually, this is also an important lesson for us to utilize the solar energy in our daily lives. I mean, it'll you know, if you work more on research in solar energy and try to harness this energy, which is just coming to us free from the sun, lots of this energy problem will be solved. Okay, so I think, you know, appreciate how this E equal to mc square comes about, and what the consequences of it are. Okay, of course, I didn't so far talk about nuclear fusion or you know, in a very direct way. I didn't talk of nuclear fusion, but then I gave you an example of fusion of hydrogen to helium in stars. Okay, but some other applications in nuclear physics, let's see if we can do such things a little bit later. Okay, so having talked of energy and mass, let's see what the expression for the kinetic energy, I mean, whatever things that we have discussed so far, whether it actually boils down to our known non-relativistic formulae. If we take velocities much less than the velocity of light. So let's check if the mass times the energy, you know, mass times the speed of light squared, from you know, we have derived the kinetic energy. Let's see whether we can get the proper limit here. Okay, so we know the expression for the kinetic energy. That's the total energy minus the rest mass energy of a body. Okay, now since we know that the velocity that we are considering here is much less than the velocity of light, so we can we do an approximation here. We do a binomial expansion of 1 minus v square by c square to the power minus half here. Okay, that's the denominator of m0 c square divided by root over of 1 minus v square by c square. What is that? Well, the first term is 1 plus, you know, the term of importance, half times v square by c square. So you plug this in the expression for the kinetic energy. Okay, it becomes 1 plus half v square by c square times m0 c square. of course, and then you subtract m0 c square from here, okay, what do you get? It's very simple, you get half m0 v squared, okay. So indeed, since the mass of the body does not change in non-relativistic classical physics, it is half mv squared, and then m being the rest mass of the body, okay. So we do see that it reduces to the classical limit at low speeds. Okay. So having talked of mass, energy, and then having seen that it actually does give us the proper limit of the kinetic energy at low speeds, let's now move a bit and bring in the momentum. Okay, remember we started this this module by talking of mass, energy, and momentum. Let's talk of energy and momentum. Okay, so how are they related? Well, you know from your previous slides here that the total energy is m0 divided by 1 minus v square by c square times c square, that is mc square. What is the momentum? Well, that is m times v, m being your familiar m0 divided by 1 minus v square by c square, okay. Well, but looking at these two expressions mathematically, you see that the mass portion remains the same, but then the only thing different is the c square for the energy part and the velocity v for the momentum part. So what will happen if we try to put them together on the same footing? Okay, what happens, for example, if we just do E squared minus P square C square? So what we do is that we square the energy, and then from that we subtract P squared times C square. Okay. Now you will check that, of course, that will have the dimension of the energy squared. Okay. But what is it? What does it give us? Something very interesting? Actually, it does. I mean, if you do the algebra, it's a rather 1 or 2 line algebra. You will see that it's nothing but when you do E square, that's the total energy, and from that you subtract P square, that's the momentum squared, times the velocity of light squared. You're going to get something very interesting. You're going to get m0 c square, whole of that, square of that, whole square of that, that is. So that's nothing but the rest mass squared, okay, of the body. Okay, so if the body has a total energy E, and it's also having total momentum P, it's moving with a certain momentum P, then E square minus P square C square is nothing but the rest mass square of the body. It's an interesting concept actually. Because what it tells you is that this group of variables E square minus P square C square remains invariant in all reference frames. Of course, these reference frames are moving with constant velocity with respect to each other. Okay. So that's what we have. We have E square minus P square C square to remain invariant. Okay. Now, well, that has the dimension of energy squared. Actually, it need not be. I mean, we were also having momentum. Okay. So we could also, in a sense, have this as the dimension of momentum squared. Well, that's very simple. All you do is that you divide the entire stuff by c squared, and then you have E squared by C squared minus P squared, and then the invariant quantity will come out to be m0 squared C squared. Now remember, m0 is the rest mass of the body, and c, of course, is the velocity of light. Okay, and this has the dimension of m0 c, that is, has the dimension of momentum, and then m0 square c square has the dimension of momentum square. Okay, so we're going to spend some time on this relation, okay, and then find out certain interesting things. But before that, let's continue a bit on these units. Okay, remember, in in relativity and in like other domains of physics, we are quite interested in units in which you measure everything in terms of something, in terms of the units of energy. Okay. In atomic physics, for example, the unit of energy is generally electron volt. Nuclear physics, MeV, okay, million electron volt. So what is that? What is EV? So EV is nothing but the energy gained by an electron accelerated through a potential difference of 1 volt. Okay. So if you take a million times of this, that's 10 to the power 6 EV, that gives you MeV, and then when you take 10 to the power 9, that's 1 billion EV, you get 1 GeV, that's a giga electron volt. Okay, that being the unit of energy. What about the mass? Well, normally you would measure everything in grams or kilograms. Kilograms is SI unit. Okay. So, however, if you consider the expression E is equal to mc squared, you can very well measure mass in terms of energy by c square. Then you can measure mass everything in terms of, in example like MEV by c square or EV by c square or GeV by c square. Okay. So that actually helps a lot. So what about the what about the unit for the momentum? Okay, mass times the velocity. If we measure velocity in terms of the how much of it is a percentage of velocity of light. So if it is MEV by c square, then you multiply by c, it should be MEV by c or something like energy by c. Well, that's very normal, because if you just consider E square is equal to P square C square plus M0 square C to the power 4, then the momentum does turn out to be energy by C. Okay, and then you can measure it in terms of MEV by C, or let's say the GeV by C if it's an ultra relativistic momentum that you are considering. Okay, now let's consider something else, one other application. Okay, it's whether one can have massless particles. Okay, and I see this as an application of relativity, because you're going to realize that in classical mechanics we kind of never asked such a question. Okay, why? Because, well, once you have a massless particle, you have matter which is massless. Well, in classical mechanics such a thing doesn't exist at all, because you see, if you have something massless, I mean, what is massless in classical mechanics? Nothing. I mean, you consider, unless you have an object which is a material matter, then you say it's massless. Of course, then the object is not there. Okay. So, but in any case, if you want to take this argument a little bit further, if m is 0, the momentum is 0, the energy is 0, so such a question doesn't happen, doesn't arise at all. So massless particle cannot exist in classical physics or in a non-relativistic situation. However, in relativistic situation, do we have a massless particle to exist? Does it, well, it's more like in classical physics it forbids the existence of massless particle, but does relativity forbid such an existence? Okay, let's just check it out. Well, if indeed the rest mass is 0, you would find the total mass to be 0 if velocity is less than c. Why? Because m0 is 0 and the denominator is 1 minus v square by c square is finite, and then that's so the total mass m is 0. And then immediately you are going to figure out that the momentum is 0 and the energy of course is 0. Fine. So if the rest mass of a body is indeed 0 and it's moving with a velocity less than the velocity of light, then massless particle should not exist. Okay. But what happens if we still have the rest mass to be 0, but the particle is moving with the velocity of light itself? Okay, it's strange, isn't it? So then what you see, is that the expression for the momentum and the energy becomes 0 by 0. It is an indeterminate form. Okay, it is an indeterminate, you cannot determine, it is 0 by 0 form. So, it is basically you cannot say that it is 0, neither can you say it is actually infinite, it is actually indeterminate, it can have any value. Okay. So, in a sense, relativity does not forbid the existence of massless particle if, and in this case and only if, it moves with the velocity of light. Okay. So, that is a very important conclusion that you can draw. It is that massless particle will be existing only and they will have energy and momentum provided they travel at the speed of light. Okay. Well, actually, can you name such a thing? Exactly, you can. It is called the photon. Okay. You know, it is the quanta of light. Okay. Then how are the energy and momentum related in this case? Well, since the rest mass is 0, then energy is equal to p times the velocity of light here, it is E times p, because otherwise E square is equal to p square c square plus m naught square c per 4. So, the m naught square being 0, so you have E square is equal to p square c square, and here so E is equal to p into c, that is what. Okay. Okay, so that is an important conclusion that we have in special relativity. Okay. Okay, so now let us change tack a little bit and return back to our energy momentum relation and see something quite interesting. Okay, so what do we have here? We have basically E square by c square minus the momentum square. Remember this, what we write as the small p, that is the 3 momentum. Okay, that is equal to m0 squared c squared, and then I write that as capital P square just to give you an idea that the invariant quantity that you have has a dimension of momentum. What kind of momentum is that? It is definitely not the 3 vector momentum that we do in our daily lives. Okay. So, that is what I said. So, the capital P here has the dimension of momentum, and then P square of course has the dimension of momentum squared here. It is different from small p. Now, what is small p? Now, small p is, let us say, it is the momentum, well, it is the 3 momentum of a particle. Okay. Now, if you take the 3 momentum squared, so the norm of the momentum, I put a vector sign on top of small p. What does it mean? It means that you take a dot product p dot p, small p dot small p, then what does it turn out to be? It is nothing but p1 squared plus p2 squared plus p3 squared. If I write, for example, px squared plus py squared plus pz squared in Cartesian coordinates, and that is invariant, you know that, because that is equal to the length of a vector. That is invariant. Okay. Even if you rotate the vector, the length remains the same. So, the vector, the 3 vector is the one in which we put the vector sign, and then we have 3 components. There are 3 independent components. Okay. Now, check that the momentum, or the we can define a 4 momentum which capital P, whose which has of course 4 components, and to keep in in consonance with the 3 momentum that we had earlier, P1, P2, P3, which is denoted by vector P. We have the first part as P0. We just call this as the 0th component of the 4 momentum. Okay. And then if we define something like the 4 momentum dot product, I put the dot product in inverted commas, and then I put a bigger dot, okay, P big dot P, okay, and all capital P's. Then we define that as P0 squared minus P dot P, the vector P dot vector P. Then we can get something quite interesting. Actually, we can relate what we have found here with the energy momentum in special relativity. So, if you identify P0 as E by C, okay, and so the total P becomes the capital P becomes E by C, and then the other vector is the 3 vector. Then the 4 vector dot product becomes E squared by C squared minus small p squared, and we know that that's invariant. Okay. Now, just like the dot product of a vector was indeed invariant, here too the dot product or the big dot product of the 4 vector is also invariant. Okay. So, there is something which is happening here. I mean, so I think if you haven't got it in these 2 slides, don't worry, I am going to talk a little bit more about the 4 vectors and space time a little bit later. Okay. So, I just want to tell you that there is something interesting that you can relate this energy momentum with things called the 4 vectors. Okay. Let us see what that is. Okay. Well, to change tack yet again and do a little bit of formal stuff in terms of Minkowski, we are doing relativity, one does relativity in terms of Minkowski space time. Remember in special relativity, so it is not only the space part, but we also have the time part which is equally important here. So, because here time is no longer an independent quantity, it also depends on the space quantities. That is what we saw in our Lorentz transformations. Okay. So, if we define a quantity, okay, an event, let us say, or the world point by 4 space time coordinates. Okay. Since the velocity of light is c, which is constant in all frames. So, what we have here is that we take capital X as Ct and then xyz. So, why have we taken Ct? So that we preserve the same dimension as the space coordinates. Okay. Or you could even make it look like you just say you have 4 coordinates x0, x1, x2, x3, and then x0 is the 0th, in a sense, 0th component of the thing called x, capital X here, and then small x1, x2, x3, these are the space coordinates. Okay. So, that is what we said, x0 is equal to Ct, and then the vector x is x1, x2, x3, or xyz if you wish in Cartesian coordinates. Okay. Now, what is the squared norm of this quantity? As we had defined, it is c squared t squared minus x1 squared minus x2 squared minus x3 squared. Okay. So, it is nothing but c squared t squared minus vector small x dot vector small x. Okay. So, what do we have? So, what we have is that in S frame, if we have a point which is denoted by one of these world space time events denoted by Ct xyz. Okay. So, a certain event is occurring at a certain time in a certain position in space. Now, the same event will be viewed by someone in the S prime frame, which is moving with the velocity v with respect to the S frame, as Ct prime and at time t prime, that is, and then the at position x prime, y prime, z prime. Okay. Remember, at t equal to and t equal to t prime is equal to 0, this 2 frames were coinciding, and then it started to move with velocity, uniform velocity v, that is. Okay. So, how are these things related? So, these quantities are actually related by Lorentz transformations. Okay. So, what is x prime? Well, x prime is nothing but, I mean, if you use the notations gamma and beta, remember we had used, we are using them so that the expressions become less cumbersome. Okay. So, beta beings v by c, okay, and then gamma becomes 1 minus beta square root over or to the power minus half, basically 1 by root over 1 minus v square by c square. Okay. Since we are moving uniformly along S prime frame is moving uniformly along the common x prime axis. And so what is x prime? So x prime is nothing but, in terms of the x quantities, it's gamma times x minus beta ct, okay, and y prime of course is equal to y, and then z prime is z, and then ct prime is gamma ct minus beta x, okay, fine. So what happens to the quantity capital X prime? Okay, so if you do c squared t squared minus x squared minus y squared minus z squared, you should check that this becomes equal to c squared t prime squared minus x prime squared minus y prime squared minus z prime squared. So the norm of the quantity x, okay, capital X, that is, of the 4 vector remains invariant, whether you are doing it in the S frame or the S prime frame. Okay. So that is what we have, and in fact that gives us the idea that if we have if you can figure out a set of 4 quantities or 4 numbers that transform as the components of the 4 vector x, okay, capital X, that is, they will be 4 vectors, okay. So and then not only that, I mean just about any 4 quantities will not be any 4 numbers, you just clump them together, they will not be 4 vectors. Well, their component should transform like the components of the space time coordinate capital X, okay, which is basically they should transform by the same Lorentz transformation. Not only that, the norm of the 4 vector that one has constructed should be invariant under any frame, okay. To give an example, just think of any other 4 vector, let us say a general 4 vector, some vector A, okay. Remember, since I am using the word 4 vector and not a 3 vector, that is what I have not put a vector sign on top of A, capital A, that is. So in the S frame, that is, it has components A0, AX, AY, AZ, and in the S prime frame it has components A0 prime, AX prime, AY prime and AZ prime, and that is the vector A prime, okay, that is the 4 vector A prime. Now if A is a 4 vector in S frame, okay, and S prime is the 4 vector seen from rather A prime is the same 4 vector seen from the S prime frame, then there are certain conditions that should be obeyed. Well, first of all, the components of A and the components of A prime should be related by the Lorentz transformation, okay. And not only that, the squared norm of A and A prime, they should be equal, and it is actually Lorentz invariant, okay, fine. So that is exactly what we had for our energy and momentum. If we define the 4 momentum as E by C, and that is the 0th part, and then the other 3 parts are the familiar 3 momentum vectors, okay, let us say the 3 linear momenta P x, P y, P z. So if capital P, that is the 4 momentum vector in S frame which has components E by C and P x, P y, P z, and then the same thing seen from the prime frame is capital P prime, and that is E prime by C, P x prime, P y prime and P z prime, the small p x prime, p y prime, p z prime, that is the 3 momentum vector in the prime frame. Then the components of P and P prime are related by none other than the Lorentz transformations. Well, this has immense consequences actually, because in a sense this will help us in relating the energy and momentum in one frame with the energy and momentum in another frame. And not only that, you can also relate energy momentum conservations directly in the S frame and the S prime frame. Okay, so more of that a little later, but then to summarize what we have talked of 3 vector and a 4 vector, let's just spend 2 more slides on it. For a 3 vector, so let's say the velocity vector, the radius vector, things like that. Okay, a 3 vector of course has 3 components, so we put a vector sign on top of that, and a 4 vector of course will have 4 components. Okay, now why is it that we call this 3 component thing as a vector, by the way? Well, it is because if you are changing your coordinate system, okay, and then you are following the change of coordinate system is due to the change of coordinate system is due to this transformation. You need this transformation matrix R to go from one coordinate system to another. And similarly, in this case of O vector, it is the Lorentz transformation which is transforming from S to S prime. Okay. Now, a vector, I mean, we define a vector to be that physical entity is that look at the 3 vector part. Okay. So, if you look at the 3 vector part and then you see that x, vector x is transformed to vector x prime. Okay. Now, it is the same transformation matrix which will do the transformation. So, the transformation matrix which is transforming coordinate system O to O prime, okay, the same transformation matrix will be responsible. It is the same transformation matrix which will transform x to x prime. Okay. So, that is a vector. Okay. And not only that, the length of this vector in the O system and the length of the vector in the O prime system will be preserved. Similarly, what you see is that it is a Lorentz transformation which is transforming the quantities in the S frame to the S prime frame. Okay. So, it is the same Lorentz transformation which is going to transform the components of the 4 vector in S frame to the components of the 4 vector in the S prime frame, just like the transformation matrix R transform the components of the vector x in O system to the components of the vector x prime in the O prime system. Okay. And just like the length of the 3 vector was constant, here what you see that the squared norm is Lorentz invariant. Okay. So, that gives you an idea why we had used this word vector for this 4 component entity in special relativity. Okay. Now, of course, there are lots of applications to using 4 vectors. We have just been introduced to 2 of the 4 vectors. One of course is the space time 4 vector and another is the 4 momentum 4 vector. Okay. Now, these are going to have applications in relativistic kinematics and things like relativistic collisions. So, let us talk a bit about such a thing, about our coordinate systems in a case where such collisions can happen, namely the laboratory and the center of mass system. So, what is it? So, basically we are considering the collision of 2 particles A and B, let us say. Okay. They are of certain they are of rest masses m A and m B. Okay. And let us say that well, you can look at this either in the laboratory system and the center of mass system. Well, in case you want to know what these systems are, the lab system is one in which one of the particles is at rest and the other comes and hits it with a certain momentum, certain momentum, let us say 3 momentum, okay, p or vector p. In this case, let particle B be at rest and then particle A is moving with a certain momentum in the lab frame, PAL, notice the vector sign and then the subscript AL, L stands for the laboratory quantity. So, whenever you see this L, it means that it is the lab quantity. So, in a sense, what is the momentum for vectors here? Well, capital PAL, that is the, we will read 4 quantities. The first quantity relates to the energy, and well, it is basically the dimension of momentum, but involves the energy, that is EAL by C, and then the 3 vector with which or the momentum with which the particle A is moving. What about PBL? That is the 4 momentum vector for particle B in the laboratory frame. Well, that is EBL by C, and then remember it is at rest. So, its total moment, that is the linear momentum, is 0. Okay. Now, what is EAL? EAL, you know that it is MA into C squared. Okay. And then what about EBL? EBL is nothing but MB into C squared. Okay. Now, remember here EAL, now when I write MA here, it is MA divided by 1 minus V square by C square actually. So, that is assumed within when I write EAL here. But when I write EBL here, remember that it is just the rest mass squared. Okay, so we conclude our discussions here today. Once we have seen the differences between the 3 vector and the 4 vector, now we realize why we call it as a 4 vector itself, keeping it, you know, some sort of consonance with this component of a 3 vector. Okay. We are going to see in our next topic the applications of this, of the 4 vector in special relativity, especially in relativistic collisions, and we will also do some more problems in relativistic kinematics in our next discussion. Thank you very much.